All right, what's going on, you guys? It's another LeetCode video today. This one's called Serialize and Deserialize binary tree. So basically, they want us to, they're going to give us a binary tree, and they want us to be able to serialize it, which basically means take the binary tree and then put it into a string format. And the reason being, kind of some context there, is like you could have a binary tree living inside of some operating system on some computer, but if you wanted to transfer it to a different system, you have all these addresses and pointers in memory that don't really matter for other systems. You really just care about the structure and the values that are in the binary tree, but you don't really care about the pointers that are specific to a device. So there needs to be a way to easily transfer that without any of the extraneous data to another system. So that's basically the context here for serialization. We also need a way to deserialize, or take a string and then construct a binary tree on a computer just from a string that was serialized. Pretty straightforward if you understand that. So I mean, they literally want us just to take a binary tree and serialize it, and then we need another function to take a string and then convert that to a binary tree. So let's look at the whiteboarding for this. So we have this binary tree here, just an example of a binary tree. One thing that I will note is that where these null pointers are, that matters because it's crucial to the structure, preserving the correct structure of our binary tree. So how are we going to do this? There's different ways to do this. The way I'm going to do it is with a recursive depth first search. I'll just have each node comma separated with a pre-order traversal, and then null pointers or null nodes will be represented with a hash. So again, there's many different ways you can do this, but the core idea of this problem is that you have to have a way to be able to serialize and deserialize a binary tree consistently, right, with whatever methodology or whatever protocol you choose to follow. So anyways, yeah, that's what I'm going to do. So this tree is basically going to look like you'd first visit the one with the depth first search. So you'd visit the one first. So let's go ahead. So this is going to be our output string here. You'd have a one, then you'd go down to the two. So you'd put the two there. And then we're going to go down to this null pointer. So null pointers, I'm just going to represent as a hash. So that's going to end up looking like that. And then we would pop back up at that point and then go right. So there's another hash there. And then we pop back up. We can now search the right subtree since we've gone as far as we can go left. Let me draw another arrow there for popping back up. So we'd see the three regular node, add that to the string with a subseeded by a comma. And actually the way I'm going to add these, now that I think about it, is I'm going to have the comma before the, I'm going to precede each value with a comma. So that's the way I'm going to do it. I'm going to have a comma before every value. That way the last one doesn't have a comma after it. But that's really, again, that's just a preference on how you implement this serialization. So whatever you do, it has to be consistent, right? That's like the core idea here. So we're gonna have that three, we're gonna have a four, we add a comma and the four to our string, and then we're gonna have those two null pointers. We pop back up and go all the way this way. Let's add those null pointers. So two hashes, and then back at the three, we've already seen that, so we're going to search right, and then finally we just have this five followed by the two null pointers. So we would go down to this five, then we would search left, pop back up, search right, pop back up, and then finally we'd pop all the way back up from our recursion. And let me finish off this string. So it would be 5 followed by those two null pointers. And that would be our string. So our serialized string would look like this. So if we wanted to reconstruct this, basically back into a tree, I'm going to do the same sort of recursive approach and do a depth first search through this array. I mean, really, it's just like a linear traversal through each number, but we can use a depth first search pattern basically to construct it in the same way that it was, or deserialize it in the same way that it was serialized. So first we'd look at this one. Okay, we know this is a pre-order traversal, so that would have to be the root node. Let me just erase this so we have room to draw it, because I'm going to reconstruct it now, or deserialize it now. So the one is going to be our root node, and I'll just I'll verbally indicate where we are in this string. So first we'd be at that one. And the way we're going to parse this, by the way, is we need to ignore commas, right? We also need to know once we've reached the end of the string, because that's when we're done constructing the tree. We also need to know how to handle hashes, and then how to convert numbers from string format back into integer format, right? To properly build the tree. So, but anyways, we'd be at that one first. That's the root. We're going to traverse, or we're going to assign basically its left child to a node pointer first, right before going to the right children, and we can see that next value is 2. Same thing, we're gonna go to the left child first. We see that it's a null pointer, it's a hash, so at that point we would set that to null pointer and then pop back up to our 2. Okay, so now we're gonna do because and that's because we know we're popping back up because the null pointers can't have any children, right? So that's why we can safely do that. Okay, so now we see another null pointer. The only thing to assign there is the right child. It's like the only option, and it's correct, consistent with the tree that we serialized. Okay, so we would pop back up there because the null pointer can't have any children, and we'd have to go all the way back up to the right child of this 1, because that is the only thing we can assign now. So we see this 3, that's going to be the root at this point in the deserialization. Okay, we have to assign the left child first. We can see that that's a 4. Okay, we're going to assign the left child first again. We see that that is a null pointer, so we have to pop back up, and we can assign the right child. That's a null pointer. There's nothing else we can do now, so we have to pop back up and assign the right child for this 3, which we see is a 5. And then we would assign the left child again, null pointer, right child, null pointer. And that's basically exactly consistent with the tree that we originally serialized. So let's get into the coding portion for this, and then we'll discuss the time and space complexity. So for our serialize function, I'm going to have separate recursive private methods to help with both of these. So let's have a private method for serialize, and we'll just call it ser depth first search. And it's going to be, for our serialization function, we want that to be void. So that's going to be void. It's just going to take a tree node, and we'll just call that, or a tree node pointer. And then it's also going to take a string, or a reference variable to a string. So we'll just call that string s. That's the string that we're going to be storing the serialized tree within. So let's go ahead and seed this function first. So we need to create a string for our serialization. It can just be empty at first. We need to call that function, right? So let's say ser depth first search, and we're going to pass in the root node and then the string, and then we can just return the string s when we're done with that. So I feel like serialization for this is a little easier to implement than the deserialization, but that was just my experience implementing the solution. So, but anyways, so for this, the first thing we want to check for base case is that, see if we're at a null pointer. So if not tree node, we can just add a hash to the string, right? So, because that's the way we handle that. So we can just say s.append, and then it's going to be a comma and then a hash. I'm going to have a comma. I'm going to precede every value that I add with a comma. So, and then hashes serve as the placeholder for a null pointer. So that would be it there. We also have to return, because this is a recursive function, and once we hit one of these, we don't want to make any more recursive calls, right? We want to pop back up from our recursion. So, so that's what we do if there's a null pointer. Otherwise, we can add the value regularly. So we need to first append a comma, because we're not going to append the value at the same time, because we need to convert the number or the integer to a string. So we're going to take that value and we need to actually put it, we need to wrap it in this toString function first, pass it through that first. That way it's converted to a string, the integer for the value at that tree node. So then after we do that, after we've added the current node to the serialized string, we can just call recursion on, call this function recursively. So let's call it on the left child first for that pre-order traversal. So 1, 2, 3, and I'm getting to, let's make sure this is a pre-order traversal first before I keep before I mess up, right? So 1, 2, 3, 4, 5. Yeah, so it's definitely a pre-order traversal. And it's a little wonky because you have these null pointers that are like included there, but nevertheless, yeah, pre-order traversal for sure. So tree node left, and then we want to pass in that string. And then we just do the same thing for the right child of tree node, and that's pretty much it. So that's it for the serialization using recursive depth first search. The time complexity of that is just going to be big O of n for all of the nodes in the tree, and then the space complexity is going to be, so let's write this, so big O of n time, and then the space is going to be big O of h, where h is the height of the tree. In the worst case, if it was a heavily skewed tree, it could be big, h could be n. So technically it could be big O of n space for the recursive call stack, but I like categorizing that as big O of h, because the tree is not always going to be skewed, right? So it's really correspondent to the height of the tree. So big O of h, and I wrote time again, big O of h space for that recursive call stack. And we're not going to count the space that it takes to store this string. If you wanted to count that, you'd have to consider that in the space complexity. But yeah, nevertheless, let's get on to the deserialization. So this is a little trickier. So we're going to need, so we have a string data that we're deserializing and turning into a tree, right? So we're going to need a couple things. We're going to need a global variable to pass by reference, basically to keep track of what index we're at in the string. So I'll call that I, and at first that's going to be 0. Apart from that, we also need, so let's go ahead and see this function. It's going to need to return a tree node pointer, a pointer to a tree node, right? So, and it's going to be the root of the tree, the very, top node, by definition, but that's the one we want to return. So tree node star root is going to be equal to, and we'll call this function deserialize, DFS, short for deserialize depth first search. So we want to pass in, let's go ahead and actually write that function signature first before I pass in any parameters, just to make things more clear what I'm actually doing. But we do want to return that root ultimately, right? We know that. But anyways, yeah, let's go ahead and write this function signature. It's for the deserialization, it's going to return a tree node. And we called it deser depth first search. It's going to take a tree node, and we'll just call it tn again. It needs that string, right? So string, and we'll pass it by reference, and just call it s for simplicity. I know they call it data in the other function, but it's going to be the same string there. And then we also need that index by reference, because we need to have this, we need to know exactly where we are at each function call, and there's no need to copy that index around. It's going to be a global value, right? So that's going to be it for the function signature. So now let's go ahead and see that recursive function here. We're at first going to, and now that I think about it, we do not need a tree node parameter because we're returning a tree node. So messed up a little bit there, but nevertheless, we're going to pass in data. And actually, I don't know, this should be fine by reference here. I'm confusing this with const reference. We don't want to make this const reference. I don't think that would work because the string is not const here. Anyways, maybe it works, maybe it doesn't. We're going to not make it const though, and just try not to modify it. So data, we need to pass in data, and then we need to pass in that integer variable I to keep track of where we are in the data string. So what we want to do first is increment I, right? Because remember, in our serialization, we're preceding each value with a comma. So just to account for that, we need to increment I first. Okay, and then we need a while loop because we need to basically remember that this is a string, right? And we can have up to 4-digit node values. So we basically need to be able to iterate through as many as 4 digits, as little as 1 digit, as many as 4 digits, right? And we have to extract that from the string and then convert it back to an integer. So we're just gonna say while our data string at I is not equal to a comma, and we also want to make sure we're in bounds, right? So let's do while I is less than s dot size, just to make sure we're staying in bounds, and s of I does not equal comma. And while we're doing that, we also need a variable for the number, a string variable for the number. That'll make it a little easier to extract that number. So we can add, we'll say num plus equals s of I, and then we can increment I, and that'll basically give us that number in the string. That'll basically extract it for us. Okay, so, and it could be a hash also. So the first thing we'll do is check if it's a hash. So if num is equal to a hash, and we got to use the string quotations because this is a string comparison. So if num is equal to hash, then we can, we want to basically return a null pointer, right? Because this node is a null pointer, right? That's what the hash indicates. Okay, otherwise we can go ahead and add the number or create a new tree node with that number, right? So let's say tree node star tree node is going to be equal to, we need to use the new keyword to create a new tree node and then take in the string converted to an integer of of num, right? So that's pretty much how we'll make that new tree node. And then we need to call recursion on the children of this tree node. So and continue deserializing the string s. So we'll just do tree node left, right? We got to do the left child first for that pre-order traversal. That's going to be equal to the deserialization depth first search of s and I. And then same exact thing for the right child, deserialization depth first search si, and then we just can return the tree node at the end, and that should take care of deserialization. The time and space for this is literally going to be exactly the same, right? Because we're traversing that string linearly, and then we're building a tree that has the number of nodes that were encapsulated in that string. So long story short, the time of this is going to be big O of n time also for the number of nodes in the tree, and then the space is going to be big O of h, same exact thing, because we need up to the number of nodes. We need to have as much or we can expect as much space as there is levels in the tree, or the height of the tree, for the recursive call stack, just building that tree recursively. So yeah, that's pretty much it for this problem. Let's go ahead and submit this code just to see those percentages. So beats 20%. Let's see if we can do a little better. But yeah, so beats 99%. It's a little better than 20, but anyways, the percentages are one thing. I think analyzing the space and time complexity with big O notation is more powerful than these runtime metrics, just because they seem to go all over the place. But nevertheless, I hope this video helped you understand this problem better. If it did, leave a like and subscribe. I'll see you guys in the next. Peace.